Okay, so it is now recording. Okay. And as I said, I'm going to use the whiteboard. All right, so you should now be seeing the whiteboard. Okay. And we're going to talk about today about naive Bayes from scratch. So first, so today I'm only going to do the algorithm on the whiteboard. In an upcoming video and lecture, you know, whatever, we'll do the actual, you know, code in Python from scratch. So naive Bayes is pretty interesting, and I had already started to lay out the foundation for this. So I remember I went over some of the intuition. I will kind of go over that again, and then, you know, just to stress the point, and then after that we'll get into the algorithm, you know, the equations, the formulas, and you'll see it's actually pretty straightforward. So let's get into it. So the name is naive Bayes. I think it's got two little dots there over the I. Naive Bayes. This is another classifier as supervised learning. Okay. Which means, as you know, that you have to have labels. Okay, you have to have labels for this to work. Naive Bayes is the, I would say, some of the advantages of it. It's pretty fast. I use it a lot like a baseline because, you know, it allows me to run it really quick. Some of it can be done in parallel, which is good. Now, disadvantages. Of this is that the accuracy or the performance, let's say, in terms of predicting, right? So let's say the accuracy, etc., the metrics is kind of low, right? Usually, in my experience, although this can vary from problem to problem, but usually in my experience, naive Bayes always does, or a lot of the time, doesn't do so well. So the great thing about that is I use it as a baseline. That's what I mean. So I know that if I'm running my data set on several classifiers, naive Bayes sets the lower bar. So basically I know, okay, there's room for improvement. If these are the scores, I can tell, okay, it does like this, and I can get the results relatively fast. So, you know, I can start doing things like, you know, logistic regression, and then I'm going to do, you know, support vector machines, and then a deep neural net, you know, and so on, right? And specialized CNNs and so on, right? Off the charts there. So that's the idea, that you start to add all these algorithms to get better results. And as I said, I always give this analogy to students, right? So if you're investing in the stock market, naive Bayes may predict your buying patterns in such a way that you lose money. Maybe you break even at logistic regression. So anything above that, any additional work with deep neural net CNNs or whatever, RNNs, transformers, just means, you know, more profit for you, which is good. All right, so now that we've got that out of the way, basically a naive Bayes, same thing. You know, this should be by now very clear in your mind. As you can see, this will never go away, right? This is, but that's great because it's pretty consistent. M by N, and this is 1, right? And our data, so sample 1, sample 2, sample N, dot, 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 feature 1, feature 2, feature 3, let's say, you know, 3, dot, 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 Fn, right? And then here you have your labels, whatever they are, 0, 1, 0, 1, and so on. And the data in here should be scaled. Okay? We haven't learned, I guess, how to scale the data. We will learn how to do that. And that's why Numpy, we need to get through Numpy more and more, because Numpy just is, you know, like magic, right? So it does so many amazing things. So now our plan is So think about it. You have a data set with features, right? So in naive Bayes, every feature gets a say in determining which label should be assigned to a given input value. So that what that means is you're going to look at F1, F2, F3 of a sample I, let's say, right? And then, so this is F1I, F2I, F3I, you know, dot, 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 Fni, right? And so you look at the feature vector of each sample, right? Whenever you determine your model here, you know, feed that in there, and the model is going to predict the class, you know, 0 or 1, or multi-class, you know, whatever, 0, 1, and 2, minus 1, 0, 1, you know, it doesn't matter. So that's the trick, right? So every feature gets a say in determining which label should be assigned to a given input. And we will see that today, right? So now the way that this works is basically naive Bayes is, you know, probabilistic. Probability. We're not going to get into probability theory or anything like that. In fact, we're going to treat this like an approximation of probabilities just by saying we know intuitively, right? You know, you guys say, well, out of the last, you know, let's take Punxsutawney Phil, right? Is that how you say it, Punxsutawney? So the little, what is it, badger or something? So he looks at his shadow and says 6 more weeks of winter, right? So apparently he saw his shadow. So this year. So, but instead of that, you know, Punxsutawney Phil, if he was, you know, more of a, you know, a machine learning person, right? So he would say, okay, I'm going to look actually at the previous 8 weeks, right? So out of eight weeks, you know, how many weeks did I see winter? Well, I saw it 6 times, you know, really cold temperatures. All right, so that then determines a probability. Maybe, you know, he sees like 4 out of 8, so that's a 0.5 probability, right? That's, you know, it's calculates some kind of frequency over a period of time, right? And then you determine some kind of a probability. So that's really it. You know, we don't have to get into all this theory or anything like that. You know, that's how you calculate simple probabilities just based on frequencies. Now, naive Bayes is built on an equation, and we're going to take a look at some of the intuition of that. But it's pretty straightforward, really. Think of it as there's an equation. We're not going to derive the Bayes equation. Okay, so you know, some very smart people came up with that, so we don't have to derive that. We're just going to use it as is, and then that just leaves the problem of figuring out the frequencies. Okay. So that's the idea. So you check the frequencies. You know, you check in naive Bayes, you check the frequency of each label. You know, each label in the training set. So, you know, obviously I'll provide an example that's the most intuitive for us to understand this, but, and I think I already started doing this the last time, right? So basically we have, you know, let's take a set of documents. Let's imagine, you know, we're kind of like Google, we have documents, we're only dealing with text, no images or anything like that. And so we have to figure out then, you know, these frequencies so that we have these probabilities so that we can use these probabilities later on, right? So let's say that we have the word run. So I'm going to take the example. This is the example I had used before, run. And we have 3 sets of documents. We have 3 sets of documents. You know, 3 sets of, you know, they don't have to be the same amount of documents. Some have a little bit more, some have a little bit less. But we have 3 sets. Right? And, you know, we can imagine they have about 2,000 words each. 2,000 words per document. And we maybe have 10,000 documents and so on, right? So these documents are going to belong to news articles related to, sports, mystery novels, and automotive. Okay, and so that's it. So we have three classes basically in our y vector, right? So we have 0, 0, 1, 2, 1, 0. So we have three classes, which are 0, 1, and 2. Okay, we have already established, we have 10,000 documents, so that's 10,000 samples. This is 1. And then we have to figure out, so we have 10,000 documents here. We have to think a little bit about the features, F1, F2, but it could be just all the words. And that's usually called a bag of words approach, where we look at every single word in the document and kind of figure out its contribution, right? So let's take that idea. So in that case, we have to determine one more parameter, right? It's not, there's 2,000 words per document, but conceivably every one of the 10,000 documents will have certain words, right? Certain words that appear in common and certain words that are unique to that document. So for instance, the word the, right? It's very likely that the word the appears in every single one of those documents. That's just how English works, right? So the, but there could be a word like Punxsutawney Phil, something like that, that Punxsutawney only appears once in one of the documents related maybe to sports, or something like that. So one of the parameters we have to establish is a vocabulary. So to do that, we have to go into all the documents, look at all the unique words, collect them, then calculate their frequencies, and select the most frequent one. So there might be a word in there that is so infrequent, like Punxsutawney, that may not really be useful, right? So that, vocabulary. Oops. Vocabulary. And the vocabulary, let's say it's going to be 70,000 words. All right, so maybe then this, and look at how big it could be. You see that? 70,000. Other question? Sure. All right. So the vocabulary could be 70,000 words. So think about that, right? For now, that's sort of how we're taking a look at this. Okay. That just gives, to put it into context into what we've been doing so far with the X and the Y. Right. So now we know that run might be, let's say run is F17 for whatever reason. It's a fairly frequent word, so it's going to have a low index number. The indices here actually, the convention is that you give the lowest indices to the most frequent words, and then 69,880 would be a more infrequent word. Okay, so we're going to look at the word run, and now for us to predict things, so it's almost like we want to predict something like this. So I grab sample 1, and I'm going to say, I have sample 1, which is, this is just an oversimplification of this, but I have sample 1. I have sample I, let's say actually I, like I did before, and I have F1I, F2I, ... F70,000 I, right? So I want to, given this, I want to predict the label, right? What label is it? Well, as it turns out, this is an oversimplification, but it could be as simple as, well, F1I, 1I, times F2I times F3I times ... FNI. You see that? So it's really just a multiplication of all the features, and then, but in relation to something, right? So in relation to labels. So obviously here we probably need to supplement with a few other things, okay? So that's what I want you to understand is the intuition to predict, the label. Okay, so that's where we're going. So it's a simplified view of it, right? We grab all the features and we're going to perform some kind of a multiplication to arrive at our goal. Okay, so obviously we need to have some information about the occurrence, the frequency of occurrence of words in documents, the frequency of occurrence of documents with relation to labels, possibly the relationship between words, documents, labels, etc. Right? So counts. How many times do we see that? So the basic intuition is to think of it this way. So, for the word run, I can say that run occurs in 12% of sports documents. Okay? And then run occurs. So run occurs in, let's say, 10% of mystery novels, mystery docs, let's say, to be consistent, and run occurs in 2% of automotive docs. Okay, so how do we determine those 12, 10%, 2%? We got it from counting frequency counts. We'll see those formulas. They're pretty straightforward, but that's something that you can do in parallel, right? You can give a certain set of documents to one computer, another set of documents to another computer. You can have a whole cluster of computers, each one calculating just a subset. And then once you calculated all the subsets, you can aggregate them and get your final results. So in essence, this part, the frequency count, can be done in parallel. And that's a good thing. Okay, so now that we've talked a little bit about that, that's kind of the intuition. I think that's as far as we had gotten the last time that we talked about naive Bayes when I gave the introduction. So now today, what we're going to talk about is some of the foundations. And in particular, the main foundation, but I should say, before I continue, were there any questions on the previous slides?
No questions.
All right, so sounds good. So now then, as I said, we're going to talk about the foundations of naive Bayes, and in particular here, there's one thing called the Bayes rule, okay? Which is going to be, as I said, we're not going to derive the Bayes rule. We're just going to assume, okay, Bayes came up with this. What's it for? How are we going to use it as our classifier? So here we're going to look at the Bayes rule applied to documents and classes. Documents and classes. All right. So we can say for a document, so we're going to define some parameters for a document in our data set, let's call it D, right? For a document D and a class, and a class C, okay? So we have the two parameters defined, documents D, class C. So the classes will be like automotive, mystery, and sports, right? And the documents will be just these 10,000 documents that we have, of which we have these documents. of which they have on average about 2,000 words. They're not super long. Some might have less, some might have more. Okay, so Bayes' rule is basically this equation. All right, it looks like this, and it's really defined as a type of a conditional probability. Okay, so it's basically the so this line just means like given. So intuitively you will interpret that as given. So in words we would say something like, what is the probability that you get C given D, right? So, you know, which is what we want to do. As it turns out, that's exactly the problem we want to tackle. The probability of C given D. Or that is to say, what is the probability that I grab this document, document X, which has these words, including the word run in it, right? And it's got the word run. So based on that, well, we had looked over here that when a document contains the word run a lot, right, like 12%, it is a sports document. But if a document contains the word run very little, it is an automotive document. So that's an oversimplification of that, but that's sort of the intuition. And if it contains run like 8% or 6%, you're kind of on the fence. You know, it's more like mystery maybe. So that's where we're going with that, okay? So the probability of C given D, so that means two things. So we almost have to say the probability, so let's say probability of, what's the probability of this? So now we want to generalize it. So I need to define this, but we want to generalize this to say, what is the probability? So I'm saying probability of C given D, right? So that's equivalent to actually saying three things. So now I have to kind of break it down into three things, and I have to say, what is the probability of, what was it, sports? What is the probability of mystery? What is the probability of automotive? Given D. Where D, of course, we have to represent D in a different way. So we really have to represent D as the words, right? So we're, you know, that's one assumption. D needs to be some kind of a vector of words. And there we have several problems because, as you guys know, to understand a document, the car is, right? You don't say is car the, you don't say car is the, right? You say the car is. So there's definitely sequence that's involved, right? There's grammar, right? There's spelling, there's, and then there's the semantics of the words together. There's the semantics of the words separately. So it could be potentially a very complex problem, very complex. But we are going to simplify. We are going to simplify the problem as much as is possible. Okay, that's our goal. Because if we try to look at all those things like sequence, car the is or the car is, that gets really makes the problem really complex. And naive Bayes is not really built for that. As we're trying to look at it right now, we're trying to actually do something a little bit simpler, right? So we need to simplify. And that's really where the problem is, right? So that, or one of the questions is, how do we get this, right? The D document. So let's kind of go over back to the equation here. So naive Bayes, the Bayes rule. Okay, so Bayes' rule. You can say that too. Bayes rule. So Bayes rule basically says that to calculate the probability of getting C given D, you really have to look at several pieces of information. You have to take the probability of the document given C, right? Because the problem is it might be more difficult to get this, right? Getting that might be more difficult, but Bayes figured out that I can simplify that problem by just calculating kind of equivalent pieces. So for instance, you know, it might be easier, instead of saying, what is the probability of C given D? It might be easier to say, what is the probability of D given C? Okay, so, and we'll take a look at that. Another one is, you multiply that result times the probability of C. The probability of C is actually, can be pretty straightforward, right? We already saw that. You know, you just count. Run. It appears in 12% are sports, right? And then run occurs in 10% of mystery novels. And then run occurs in 2% of automotive documents, right? So out of all the documents, right, we're distributing it into the classes, for instance, right? And so that is actually doable. We can actually do that one. Whereas this might be, you know, extremely hard to figure out without intuition. If we break this as an equivalent equation to several parts, those may be easier to calculate. Also, we can look at the probability of just a document, right? So out of all the documents, you know, this document, you know, what is the probability of it, of its occurrence in the data set? So we'll take a look at the meaning. So we want to take a look at the meaning of these. All right, and we will do that. That's basically where we're going with this is, you know, what is the meaning of all of these parameters? But as I said, I don't really want to go beyond this with Bayes' rule. And instead, we're just going to pick up here, right? So we're not going to derive where this came from. We just assume, okay, if we want to get this value, Bayes figured out that it might be simpler just to break it up into these three parts, and these values might be easier to calculate. And then once you have those values, you can basically infer probability of a class given a document. Okay, does that make sense, guys?
Yeah.
So then the idea then, if we have those pieces, all right, we can start with that equation, right? So we can start with probability C given D. Bayes' rule says probability of D given C, probability of C, which is the class, and the probability of D. Right? So we still need to figure out what those things mean, but from here now we can derive then, start to figure out a classifier, which is going to be our algorithm. Okay? So our algorithm then says we want to select the maximum probability. All right, so what is the maximum probability? So the function becomes argmax here. Argmax. Right, probability of C given D. Okay, so that's really what we're trying to figure out is for each one, we can look at, I have a slide for this. So if we go back to, we should be seeing bright space now. When we click on naive Bayes here, you can see in the slide, I kind of have this in here. So we've talked about, okay, I think I need to download it. Hold on. All right, there it is. All right, so we are looking at, you should be seeing the slides now, and you can see here, so this is what we're talking about. We're talking about predicting a class given the features. I've set this, we talked about the probabilities. We talked about this. And basically there's your Bayes rule applied to documents and classes, right? So you have basically here the same thing. So we need to compute this formula for all classes, okay? We need to compute that, and that's the key parameter. We need to compute this formula for all classes. In our problem, we're simplifying this to 3 classes, okay, which are the sports, mystery, and automotive. So really, for every document that we get a document. I get a document, you know, whatever it is. And then now that document, I need to calculate, okay, it's sort of like, is this document class A? Is this document class B? Is this document class C? Okay, so that's an important element. We need to compute this formula for all classes. So the classifier then becomes, it can be generalized to be something like this, right? So predicting the class, you could also say, you know, something like I here, right? So given a document, we're going to calculate for where I, you know, is defined as, you know, our 3 classes, right? 0, 1, and 2, which are automotive, mystery, and sports. So we calculate those 3 equations, if you will, for the 3 classes, and then we find out of those 3, whichever one has the highest probability wins. Okay, whichever one has the highest probability wins. So basically, if we go back to our notes, all right, so we need to compute this formula for all classes, right? And so we derive in our whiteboard, we need to say, well, if this is the equation like this, we need to get, you know, we need to find the highest probability for the given the 3 classes. Now, since we already said that that's what we want to predict the class given the document, but that's a hard problem to do. But because of thanks to Bayes' rule, right? Thanks to Bayes' rule here, we can instead change that a little bit. So if you look, instead of using this one like that, I'm going to change the equation to be predicting the class, the maximum, right? Given, instead of this, you know, probability of C given D, I'm going to rewrite it as probability of D given C times the probability of C divided by the probability of D. So this is the probability of C as in Charlie. All right, and now I've incorporated in my equation the formula that you know, the Bayes rule, basically. Now, there's going to be from here some additional simplifications. If you think about it, there's going to be some simplifications, but we are going to arrive at, and I'll elaborate. This actually can be simplified because if you think, okay, now I have to calculate. Let me go to another page. So if now my formula is like this, argmax for each, I have to do this for each class. If you think about it, that means I have to get this piece of information, this piece of information, this piece of information. That's a lot of information that you're getting there. As it turns out, we can simplify this, and I'll show you how we do that, but it can actually be simplified even further to just argmax probability of D given C probability of C. So basically, I get rid of that term. And that's a good thing because by getting rid of that term, I have fewer things to calculate. Okay, guys? I have fewer things to calculate. So the question is, you know, why, how can I get away with that? So we'll take a look at that in a second. All right, so let's go back to the slides. Right, to follow along. So here we have our classifier. We have to calculate, you know, the intuition there. We compute this formula for all classes, all 3 classes in our case. So there's the formula, and then we arrive at this one so far. And now think about it. Really, that formula, the previous one, as I said to you, needs to be calculated for all 3 classes, right? So if you think about it, we have to do C1, right, which would be, let's say, this would be for sports. C1, this is mystery, and this is automotive. So when you have something like this, you guys should probably remember that they have a term in common, right? Which is this term. So we got something like A times B. We got A times B multiplied times 1C, let's say, right? So all terms have this in common. So this is a term that because they have it in common, we can just cancel it out. You see that? Because you actually have to calculate the probability of D is not dependent on C. Do you guys see that? It's only dependent on the document. And so every time you do this equation, actually, it's always going to be the same value, the same term. You know, it's probability of how many times, and we don't even need to figure out what it means, right? We just need to say, okay, that was C. It's always C here, it's C here, it's C here, right? So that's a term that is common to all, and therefore it's not going to affect, you know, it's going to be the same value. So things are going to stay the same. So if we calculate, you know, let's say T1, T2, T3, they're all being multiplied by the same term, A, right? And so we can cancel that out because it's a term that they have in common, and that just allows us to arrive at the simplified version of the equation without the probability of D. Does this make sense, guys?
That makes perfect sense.
All right, so yeah, so that these are the beautiful things sometimes about, you know, machine learning and doing these things that you might think, oh man, I have to do all this work, and then you realize, okay, wait a minute, you know, this value is a constant, right? Or this value is common to all, we don't need it. So you get rid of it, and now you simplify the equation to these 3, right? So you simplify it really to these 3, which I'm just generalizing it to saying, you know, this one over here, right? So we can go then back to our slide, or sorry, to our notepad here. And now we know how to, you know, get rid of that one. It's pretty great. So then we have C1, C2, C3. So for every document, you know, this is going to be, it's really argmax of these 3, but I'm just going to write it like this. Okay, and now we just have fewer terms. We have the probability of D given C1 times the probability of C1, and the probability of D given C2 times the probability of C2, and then finally probability of, you know, what is the probability of D given C3, probability of C3. So we now all we need is these 2 parameters. We need this parameter, that parameter, right, for that one, and well, all 6 really. But we need those parameters, and once we have those parameters, you know, we're good. We're good to go. All right, and now we can do our algorithm, basically. So that's really the idea. So now let's just for kind of to be thorough, I'm going to name what these things are called, okay? So usually they have, because you might see this, I can say probability of D and CI, probability of CI. And this is called usually like maximize the probability. All right. This is called, this term, right? This one here is called the likelihood. What is the likelihood? Okay. And then this one usually is referred to, this one here is referred to the priori, right? That's just some information. It's not really relevant to our algorithm, but when you're writing your algorithm, if you want to call these by those names as variables, that could help you a little bit. Okay, so now the question is, so we're pretty much done with that. And now we have a working algorithm, and now what's left is we need to define this parameter and this parameter. Really, that's all we need to do. Define that so that we know how to compute these. At the end of the day, you're going to end up with some kind of either an SQL database or a dictionary in Python, some kind of a structure like that you can store somewhere so you can pickle this right into a file. If you remember from oh, this is a 140 topic, but yeah, so pickling is saving a dictionary back to a text file without having you just save the whole thing like a binary, or you store it in a SQL database. It really in machine learning, I want to stress in data science, applied data science, SQL is still pretty important. So SQL is not just for websites, right? So if you guys have thought about, okay, I usually use it for my website, but remember that it's data. SQL is just data, and it's extremely efficient and good. And so a lot of people get their data from SQL or something called NoSQL databases. That's, but somewhere where they store the data. And so you would need to get those frequency counts, which, you can think of it as a table of a lot of, okay, how many times did I see this document associated with this class? So you calculate that probability and so on. And that's what we need to define now. So that's our next step in our algorithm. And we have plenty of time to finish it today. So let's go back to the slides. I just want to make sure I'm covering everything. So I like this slide. I think this is a very good, you should be seeing, sorry, you should be seeing the slides. So this is a pretty good slide here, which kind of can be summarized with this. Now the next question is this. So as you know, if we want to calculate, so we're going to focus on probability of D given C, right? That's what we want to get. So the first thing, we kind of have a notion of, okay, what is C? So it's the number of times we see the class in the data set, for instance, right? So that, but what about document? What is document exactly? We need to represent that. So the way that we do document, initially it's going to be a text file, right? So some kind of text file. Imagine if you get something from the Gutenberg, what do you call it? The Gutenberg site, right? And they got all these UTF text files of stories, a lot of stories. So really that's something you can think of as the source. So it's really a document of words. The car is going really fast, or the car is running well today, and let's say there's about 2,000 words on average in these documents. So we need to take each document and we represent the document as features. And this is going to be called the bag of words approach, all right? It's not the most efficient way of representing the document, but it's been traditionally, the first thing people always do, okay? And that's kind of what I had mentioned before. So what that means is, if we go back to here, is that we have a document of 2,000 words, and now we need to find in all the documents, so we need to look at all 10,000 documents, find out the vocabulary, as I said, the 70,000 most unique words in the vocabulary, right? And the most frequent. So we take all the words that are unique, and then we calculate, their frequency, and then we kind of rank them. And then after ranking them, we have basically a set of the most frequent words. So we're going to take then, for every document, we're going to represent it. So I have document 1, document 2, document 3, all the way to document 10,000. And we're going to represent these as feature vectors just of the words themselves. So again, you can think of as F1 equal, let's say the, F2 is going to be car, F3 is, ship, F4 is cat, and so on, dot, dot, dot. Fn could be something very infrequent, punk, satani, whatever, right? And so you get that vocabulary where this is, about 70,000. So it's a very high dimensional space of your, but all documents are represented then by each word. And what does that mean? It means that if the document contains the word, what do you think you would do to the vector? You can put a 1, right? So you say, well, document 1 does have the word car, right? And it does have the probably, but it doesn't have the word cat. It doesn't really talk about cats. So that's a 0. Now, another thing is you could say, well, it contains the word car actually 2 times. All right, so that's what the bag of words approach means. So in the next document, the is probably in every single one. So if you look, the fact that the word is in all documents actually tells you that this feature is not very good, because machine learning is about differentiating features, right? Or correlating them to classes. But if a word appears in all documents, it's probably not very good. But the word car might appear here just once. Here it doesn't appear at all. Here it appears 3 times. Ship appears in this one 5 times, in this one 7 times, in this one 0 times, and this one 1 time. And the word cat actually only appears in this one 7 times, and then in the other ones very sporadically, and so on. Does this make sense, the bag of words approach, guys?
Yeah, that makes sense.
All right, great. All right, so that's, once we have this is the key thing, right? Because this is how we represent each document, all right, through this idea of the bag of words approach. So we represent this idea as the bag of words approach. Now, once we have this, it means that for every document, we can grab a document, because remember, we need to have probability of D given C. So we need to have some information about the document. So really what we're saying is we're representing a document as a subset, of words, of the words that appear in that document. Notice here, this one, for instance, doesn't have those 2 words, right? So that document 3 does not include car and ship. They're not there. And so that's very important to our algorithm. So if we go back to the slides, then we can see here, we represent the bag of words approach. And now the next question is, how do we feed that document into, how do we feed the document into the formula, right? So that's the next question. Okay. So here basically then, we're going to say that whereas before this was probability of D given C times probability of C, now we need to make a new interpretation. Well, we know that D is actually a vector, not of a document itself, but of its words, right? So we know it's actually feature 1, feature 2, dot, 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 feature N. And we know, 1, zeros, whatever it is. So if I rewrite it as X's, then X represents the words. So now I'm going to say the document is going to be represented as X1, X2, X3, all the way to Xn, the words themselves. So I can plug in, instead of D, I just plug in the words, the features. You see that? So, but there's still some problems with this. That's really all we know, that we have those words. So we still need to figure out how to account for this, okay? Now, as far as the probability of C, that one is a little bit more straightforward. The interpretation is basically, how often does this class occur? Okay, it's as simple as that. In my data set, how often do I see the class automotive? So out of all the documents, how many are automotive? How often does this class occur? Out of mystery, out of all the documents, how many are mystery, right? So that's not so bad. This one still needs work, probability of D given C, but we know that we can represent D as just a combination with the bag of words approach, right, of the words. So that's the next thing that we need to think about. So talking about the bag of words approach, so how do we get these frequencies? We basically count the frequencies in the data set or the corpus, okay? So for instance, here I have the example, the car is going fast, and so we're gonna take, with the bag of words approach, we indicate, okay, we have two examples here, car going fast, it's there. And then it's the same vector over here, car going fast, but for a different sentence. Now, what's important to notice here is that the car is going fast and the fast car is going kind of have the same meaning, or actually they don't have exactly the same meaning, right? The car is going fast could be a Beetle going really fast. The fast car is going could be a Lamborghini going really slow, right? So meaning-wise, they have different meanings. The point of this is actually to notice that the bag of words approach loses some meaning. Do you guys see that? Because we will represent both of these documents, one talking about a Beetle that's a slow car going fast, one talking about a Lamborghini that could be going slowly. But they both get the same representation in the vector. Do you guys see that?
Yeah.
Yeah. So that's important. So in NLP, really, order does matter. However, what I'm saying here is that we have to make some simplifications, some assumptions to make this algorithm work. And so we lose some of that meaning, okay? So that's an important essence. But we still, at least we know that now we are representing documents as vectors of features of the vocabulary. So here we have then the assumptions. Well, we have D, right? You can see that there, represented as the words. So assume a bag of words approach, which does lose, which loses meaning. So therefore, we get rid of order, right? We lose that, as in the previous example. And, we have another problem, right? So we have, still we have P, X1. Well, let me do that. We have D as X1, X2, X3, right? And we kind of lost meaning, but there's also the assumption that if I say, the rocket booster is in orbit and it's taking pictures in space, you can kind of say that space and orbit, meaning-wise, you guys know those two are correlated. There is a relationship, right? There is something. That is also lost with the bag of words approach. And so when we say that, we're basically saying it doesn't matter. We don't care that orbit and space are somehow related, okay? We're gonna simplify our problem even further by just taking the assumption the words are independent. The advantage of that is that whereas before we had one set, this was like, like a set of, we had the problem that this was like a set of tennis balls in a mixture of clay. They were just like one entity. And so how do we represent that as this? That was the big question, right? You know, that's kind of complex. So we will make an additional assumption that the words are independent. So it doesn't matter that space, we know space and orbit are related. We just assume they're independent. And that allows us, so I use this analogy, that allows us where, you know, where this is, the document is this whole thing, but these are the words. That allows us to treat each word independently. Okay, so now that's good, that's useful because it allows us to simplify our equation or our, you know, this parameter. So we need to modify this parameter, which became, you know, x1, x2, x3, dot, 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 class. We need to simplify that still even further, okay? And so we make these two assumptions, and that results in the following. Because of that assumption of independence, we basically are able to derive everything that we need. Now we go from this one, which was pretty complex, to this one, which is actually not complex at all. Do you guys see the difference? Whereas before we had to calculate, you know, the probability of whatever this is given C. Now we don't do that. We just independently treat every X. So now all we need is the probability of a word and every word I given the class. And that is something that we can easily compute. And all we have to do is then we multiply the terms. So if we had x1, x2, x3, all the way to xn, now we end up with the probability of x1 given C times the probability of x2 given C times the probability of x3 given C, dot, 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 times the probability of xn given C. And that is the ultimate simplification because it allows us to go from this blob that we don't, you know, we don't even know what that is, to something that is easily calculated. And it turns out that still, you know, even though that we have this huge simplification here, as I said, the algorithm naive Bayes sometimes does extremely well because you don't need anything more complex, and at least it serves as a baseline. And in mathematical notation, we represent a multiplication, right? If you notice, just that parameter can be written as this part here, right? So this just stands for multiplication, okay? This just stands for multiplication. So it means that of all the x's, we are going to multiply from 1 to n, which is 70,000, right? So we multiply the probability of probability of x1 given C times the probability of x2 given C times the probability of x3 given C all the way to times the probability of xn given C. Sometimes x is a 0, right? It's not there. As you know, when you multiply times 0, the whole thing becomes 0. So we do need to do an additional little trick for that. But basically, we're going to figure out that whenever the word is not there, we just discard the parameter. And then once we've calculated all of that, we just multiply times the probability of the class. Questions, guys? All right, so that's basically the idea. So let me go back to the slides here, or the whiteboard. So kind of to repeat then, right? So we, you know, just to kind of drive this a little bit more. All right, so we have then probability of C. How often does this class occur? All right. So that's something we can get. So we just count the frequency in a corpus. That's all we have to do, right? So we calculate the frequency in a corpus. We are assuming a bag of words approach, so that gets rid of order. And we also assume, so, we get rid of order. And we assume the features, which in this case are the words, right? So the features, which in this case are the words, are independent. Right? So we assume the features are independent. And so now, what we had the two terms, right? So we had probability of x1, comma x2, x3, dot, 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 xn, given c, and we would multiply that times probability of c, right? And this, as I've said, this is a kind of an unwieldy monster that we don't even know how to characterize. But because of the independence assumption, we can just say, well, you know what? This term here can just become the probability of x1 given c times the probability of x2 given c times the probability of x3 given c dot, dot, dot times the probability of xn given c. And that is a much more easier thing to handle. And then this is summarized, if we want to take these two as, the formula then generalizes to we have to do this for every I, right? So argmax, so generalize CI to argmax probability of C, which that, it's pretty much this one, right? So that doesn't change. But now we have this other component represented, this is going to be a multiplication, okay? So here multiplication, and then this just implies the multiplication for all x's, all the words, and its probability of x, right? So let's say here, actually, let me use I here. So it's going to be I equal 1 to n, which is 70,000. So it's going to be probability of xi given c. Okay? So now, independently, you treat all of those, and you just need to have. So in the table, you literally need to have, okay, how many times did I see run with automotive? How many times did I see run with mystery? And if you think about it, this is exactly where we started, right? So we started with this idea. Oh, sorry, not there. We started with this idea, right? We started with how many times do I see run in sports? Those are the classes. How many times did I see run in mystery? How many times did I see run in automotive? So that's exactly what we arrived at here, right? How many times did I see run with automotive? How many times did I see car with automotive, and so on? Okay, so this then gives us our ultimate equation. So really, when you do the algorithm in Numpy, for instance, you don't have to, everything that we've done, everything that I did is just kind of the explanation of going from base rule to this. But really, all you have to implement is this one. You see that's it. So it's pretty straightforward, really. It might look complicated, but it's not, right? It's not really complicated. So now the question that remains is, how do we get those probabilities? Right, so how do I get those probabilities? So if the equation is this one, I need to find this parameter and this parameter. So I need to have all of these parameters, okay? And so that's the question here. How do I get these probabilities? And basically, the answer is simply count. So what do you count? Count the frequencies in the data. So you're going to need the probability of all CIs, right? So you need this one. And you also need the probability for all words given the class. So Cij. So you need to calculate those. And that's it. So we need to then now, the last piece of this is to define how this will work, right? So how does this work exactly? And so we can basically start with the first one, the simplest one, which is, and I usually like to do this in one single line. So let's start with probability of C. Let's use J actually for the classes. So probability of Cj, right? So what is it? It's a count, right? So first of all, let me just write it as doc count of Cj. Let's write it like that. Divided by n doc. Okay, so that would be how we do it. So now we just need an interpretation of what that means. So n doc, pretty easy. Count of all documents. What's the count of all documents? We already have that parameter, right? How many documents do we have? 10,000. You remember that? So that's pretty easy, right? So the count of all documents, and that's already very easy to figure out. Now the next one that we want to take a look at is the top one. Let's call it doc count Cj. And this one, intuitively, we can describe it as how many documents, how many of the documents, are in class J. So how many of the documents are in class J, which we can also figure out, okay, you know, these documents were automotive, these documents were mystery, and so on. So that is basically it. You just have to implement functions to count these, and you've got your parameters for PCJ. And then once you do that, you just save them in your dictionary, your text file, your SQL database, you know, what have you. Then so that's really, that takes care of this one. That's done. And it means that we have this part. Now we just need to figure out this part here, right? We figure out that part. Our algorithm is complete. Okay, so now I'm going to go ahead and take a look at this one. So now what is the probability of each word given Cj? So I'm going to go over here and I'm going to look at the other one. So I'm going to, again, probability of the given word, Wi, given Cj. Okay, so what is this one going to be? So we're going to do the same thing. I'm just going to write the equation. So let's just say count Wi, comma, Cj. All right, and then we just have to intuitively define what this one means, divided by the sum of all W's exist in the vocabulary, right? So here we have it's going to be a count of Wi's, comma, CJ. Okay, so that's the idea. So now we need the interpretation of this, which is very essential to understanding. So we're going to say, okay, the denominator here, what does that actually mean? Okay, so the denominator, what does that actually mean? Well, the denominator means the total number of words in documents of class J, right? That's basically what you need to get. All right, so you need the total number of words, right, in documents of class J. So first you need to find all the documents in class J, you grab them, right? And then that's a subset of all the documents, so it's only the documents of class J. And then out of that, you calculate the total number of words in there, right, in those documents. And that gives you, so that's what this is, right? So count, in that given class, what is the total number of words? The numerator is going to be in relation to, so for the class, we have all the words. Now we want to look at individual words, WI. So here we have the total number of words in documents of class J. Now we're going to look at individual WI. So we're going to say the count, let's say, count how many times WI, a given word, WI, occurs in documents of class J. Okay, so that's basically the idea. So count how many times WI occurs in documents of class J. So whereas here, if you notice, whereas here we look at all documents of class J and then all the words, here we only look for a given word, count how many times WI occurs in that same group in documents of class J. And that's it. Once you have these two parameters, you can perform the equations, right? You calculate all the frequencies, and then you just go back to your formula, you plug in the values, and you pick the one that has the highest probability. Now, of course, if you multiply, we know that some of the features will be zeros, right? Like these, right? So if we multiply everything, one thing times 0, it all becomes 0. So to address that final issue, we need to do a little trick. So we're just going to generalize this to be probability of WI C, for instance, is going to be, count WI C plus 1, so that, it doesn't become, if it becomes 0, then it becomes 1, right? And so we don't worry about it. So count WC and also plus 1. And this is a, standard computer thing. So that, or, computing thing, I should say, so that things don't become zeros, right? So you just add that 1 in there. It's a multiplication. It just ignores the term, but it doesn't kill the whole multiplication. So if probability is 0, then multiplication, you know, by 1 basically. And that's pretty much it as far as the algorithm. So let's go back to the slides just to make sure I didn't miss anything. So as you can see, we were here. So now we generalize to our equation, right? And then the final question was, how do we get these probabilities, right? So you're seeing the slides right now. All right, so the answer is you count the frequencies, and so we need to define probability of Cj and the probability of a word given the class. So that basically is what I said before. So here, how many of the documents are in class J? It's the numerator divided by countable documents, and then this can be summarized a little bit like that. And then the other one is the probability of the word given the class. So you can see here, count of how many times WI occurs in documents of class J plus 1. You can see the plus 1 there, divided by the total number of words in documents of class J. Okay, so that's basically it. And this just shows a little example of how the ones help to avoid problems, problematic things like that. All right. So then, yep. So that's basically it. We're not gonna do this right now. That's just from I forgot to erase that. Right. Yeah. So that's the algorithm of naive Bayes. At this point, really in summary, then, as I said, going back to our here, right? In summary, all you need is this, right? All you need is that. That's the algorithm. To calculate, you have to do that for every class, like we indicated here, right? So if you have 3 classes, you have to always run it, and you pick the highest one. So that's what the argmax means. You pick the highest probability. Okay, and then the other component is you need to figure out these probabilities here, what they mean, and that's it. That's basically the naive Bayes algorithm. Are there any questions, guys?
Not from me.
Questions. All right, good. So that's good. So this is this is one of the algorithms. Not all algorithms are like this. So this is one of the few. If you notice, we didn't do anything with like geometry, right? So if I give you a context, just kind of put this into context here. So far, we've said that you always have X and Y, and you have, something like this. N times N, M, N times 1, right? These are the samples, these are the features, and these are the classes, the labels. And so now we have 2 algorithms, K and N, and naive Bayes so far. If you notice, they take the data the same way. So they're both really represented in the vector space model. However, K and N was more of a geometry kind of an algorithm. If you remember, we were, calculating we have points, right? And then we have these ideas of distance metrics. So we calculated distances, etc. This one, naive Bayes, didn't really follow that type of approach. It followed more of a probabilities, conditional probability, D given C, right? So it followed a different approach, but as far as the initial representation of the data, it doesn't matter, right? We can always represent it. And that's a great thing about this. We always represent the data as X and Y. And then from there, we can apply it on a KNN algorithm or a naive Bayes. Now, most of the algorithms that we're going to study are more geometrical, okay? So they're more geometrical like this, and they're not going to be so probabilistic like this one, okay? Although the ideas are there, the probabilities are there in some way, what I'm saying is the intuitions will be a little bit more towards this. The more, you know, for whatever reason, the more powerful are represented as this idea of geometries, distances, you know, separation boundaries within a space, etc. Okay, so that just gives you a little bit of context now. So we've got two algorithms, right? And we can't cover all, but certainly I wanted to cover these two. You know, so now we've got a little bit more going. Good. We will, so that's basically the theory of naive Bayes, you know, kind of the foundation where it comes from. The next thing we need to do, which we won't do today, is to look at the algorithm. So very much like we did with KNN. So with KNN, we went over the theory of it, you know, how it worked. Then we implemented it in, you know, Python from scratch with Numpy. My goal now is we've covered naive Bayes, theory, the intuition. In the next time, we'll do the Python implementation of it. Okay, and we'll continue doing kind of that same approach, going over theory, and then the implementation of it. All right, so that's basically then, at this point, I don't have anything else to say about naive Bayes, okay? So we have about 10 minutes, so what I'm going to do now is we can just go over, you know, use the remaining time kind of to practice a little bit more of the Numpy, okay? So let me just do that. Questions? Feel free to ask questions if you have them, guys. All right, so let me. Okay, so I'm going to bring up the Numpy examples, given that we're going to be doing probably a lot of Numpy all semester, kind of like this, because there's just so much of it, but I think that actually works out really well. I'm going to open up the Jupyter Notebook. Oh, also, you know, I'm going to save that. Hold on, I'm going to save this PDF and just load it. Okay, so this, just in case, you have the slides. This is a little bit repetitive, but at least you'll have the PDF as well if you want to print it. Okay, so give me a sec here. So this will be naive Bayes. All right, so that naive Bayes document I'm about to load on here. All right, so there it is, naive Bayes PDF. So that's now loaded on your Brightspace, I believe. So if you click on it, yeah, you can see there some of the notes, same notes, similar. All right, so the document is there, so that's good. So let me switch over to All right, so you should now be, so we'll just do a little bit, given that we are, we just have like 10 minutes left. So let's look at, so you should now be seeing the Jupyter Notebook, okay? And I strongly recommend that you continue to practice these, okay? So I think we were on Numpy examples. All right, so this is where we were. All right, so we got as far as shifting. Okay, so shifting was one of the last things we covered. Yeah, so shifting. Then after that, we started extracting vectors. So I remember that also. So we extracted, we wanted to get the 2, 6, 10 here that you see. So the second column. And so we slice it out by, all rows and then column 1. If we wanted the second row over here in this part, then we could do A, again, we grab 1, 0, 1, so the second row, and then all columns, and that gives us 5, 6, 7, 8. So that's where we are. So I just need to run this one to get the Numpy initiated. So we did a column, and then we did the row 5, 6, 7, 8. Okay. So now we can take a look at slicing in Numpy. Okay. So a little bit more here. I'm going to say that slicing does not copy. All right. So slicing in Numpy, I should say in Numpy, I guess. In Numpy does not copy the array, but instead still modifies the original. So if you want to copy, so if you actually want a separate object, right? You want to like copy, so to copy a new one that's totally independent, you use the dot copy function basically, or method in Numpy. So, let's take a look at an example. I'm going to grab that same A here, copy, right? So I have, the 3 by 4 matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so now what I want to do is I'm going to create a new underscore A, and that's going to be, let's say, A, the original A. I'm going to slice from beginning to 2, comma, and also from beginning to 2 for the columns. All right. Now I'm going to print it, of course. I'm going to print A, and I'm going to print new A. So we can take a look at the difference. So print A and new A. So we're going to run this one. And you can see I've got 1, 2, 6, 5, 6, right? So I extracted that from the matrix there. Now the question is, we're talking about copying, right? So let's go ahead and do, I'm gonna grab new A, oops, sorry, new A, right? Which is 1, 2, 5, 6. And for this one, I'm going to say that I want the parameters 0, 0, right, to be changed to 42, right? So I'm going to change that number. Now I print it. So now if I print new A, first of all, right, run it, you can see the number has been changed as expected. But what happens to what happens to A itself? So if I run print A, guess what? A has also been modified to 42. And maybe that's not what you would have expected, right? You would have expected when you slice something out of something that it would have been two separate entities. So just keep that in mind. So instead, if you want to keep them as separate, what we could do is you could do new A2, right? So we have a new one, new A2. And it's going to be A, all right? You know, 2, the same thing, 2, 2. So we extract the same thing. But now you want to say dot copy. Dot copy. Okay? So now when we do this, and when we modify new A2, and we're going to do the same 0, 0. We're going to change the number to 17. Okay? 17. So now if we print new A2, obviously it'll have 17 in there. If I do print new A2, there it is, 17. Now the question is, in the old one, A was 42, right? 42. So it should still be 42 because this is a copy. So I'm going to print A. All right, run it. And if you notice, it is in fact still 42. So here I have an actual copy. So the number pretty much stayed. You know, this is a new one, right? So it stays the same. Make sense, guys? Questions about copy?
Nope.
All right. All right. So I think, you know, we got through that copy one. That's good. Then after that, we're going to look at reshaping, and that's a very important topic. So I'm just going to save that for the next class. Okay. But whenever we have time, we'll squeeze in a little bit of Numpy. I think that actually is not a bad idea. All right. So that's it for today. All right. So I'll start generating this video, and I'll post it later tonight. You got the PDF already. So also KNN, consider it officially assigned, and it's due a week from today, okay? So please work on that assignment. My goal is not to give you any more of that and for you to just solve it on your own. If you have any questions, email me, see me during office hours. But, you know, I really want you guys to get that one fully functional. All right, so that's your homework number 2. And then we'll see next week probably about homework number 3 as we start moving further into the topics. Okay? All right, so I'll stay a couple of minutes if you have questions. Otherwise, we'll stop here for today.